Have you ever dreamed of a circuit component that could measure a voltage without drawing any power from your signal source? Imagine observing an electrical signal without disturbing it in any way. This is the magic we often seek in electronics, and it leads us to a fascinating concept within ideal operational amplifiers. In an ideal operational amplifier, or op-amp, zero input bias current means that absolutely no current flows into or out of its input terminals. This is a fundamental characteristic that simplifies circuit analysis and allows the op-amp to function as a perfect voltage amplifier without impacting the source it is connected to. The core reason behind this zero current characteristic lies in the ideal op-amp's infinite input impedance. Impedance, in simple terms, is the opposition to current flow. When a component has infinite input impedance, it means that any attempt for current to flow into its inputs is met with an infinitely large resistance, effectively preventing any current from entering. Think of it like trying to push water through a completely blocked pipe. No matter how much pressure you apply, no water will pass through. This theoretical perfection ensures the op-amp does not load the circuit it is measuring or amplifying. For you as a designer or student, this characteristic simplifies calculations immensely. When analyzing circuits with ideal op-amps, you can simply assume that no current paths exist into the input terminals. This allows you to apply Kirchhoff's current law at the input nodes, knowing that the current entering the op-amp itself is always zero, which is a powerful simplification for nodal analysis and understanding voltage relationships. This concept is closely related to the idea of a perfect voltage buffer, where the op-amp precisely copies an input voltage to its output without drawing any current from the input source. While real-world op-amps have very small, but non-zero, input bias currents due to their internal transistor structures, often field effect transistors, are used at the input stage to minimize this effect. This reduces the error voltage caused by current flowing through external resistors connected to the input. Understanding zero input bias current empowers you to design and analyze circuits with greater confidence and accuracy. It is a cornerstone for comprehending how op-amps can precisely amplify and condition signals without inadvertently altering the very signals they are meant to process. This theoretical ideal provides a foundational model that makes complex analog circuit design more accessible and predictable, moving you closer to creating truly robust electronic systems.